So, today we will talk on properties of refractory. As you recall from the earlier lecture, in metal extraction industries, several diversified requirements of the phases are there. There are liquid phases. Among liquid, there are molten metal, molten slag, molten matte, hot gases, solids moving at different speeds, different viscosity, different temperature. So, what I wanted to say is that now we have to look into the property of the refractory which are available to us, so that for a particular application we can integrate some of the properties or the properties which are required for a particular application, it can be determined from that. So, the first property that is important is refractoriness or fusion point. Refractoriness or fusion point. Now, this is the temperature at which a refractory will deform under its own load. Remember, refractoriness is a temperature at which a refractory material will deform under its own load. That is important. It just begins to fuse. That is the point at which the refractoriness is determined. And this refractoriness or fusion point is commonly expressed in terms of pyrometric equivalent cone. Pyrometric cone equivalent. That is, out of the refractory material of which you want to determine the refractoriness, a cone of certain standard dimension is prepared, it is heated, and the point at which it begins to fuse, that cone is taken out, it is compared with the standard cones, and from there the fusion point of the refractory is determined. Another important property that is important is the refractoriness under load. Refractoriness under load. In a short form, it is called RUL. That is, here it is the temperature at which the refractory begins to fuse under a certain specified load. That is, a certain amount of load is applied on the refractory, and then the refractory material is heated, and the point at which it just begins to fuse, that is the refractoriness under load. Now, remember, refractoriness under load or the so called RUL is the most important property of a refractory, particularly when the refractory material are subjected under the load. For example, you are constructing a brick wall. So, for the construction of the brick wall, the refractory material which is at the bottom, it is subjected to the load of the entire column of the refractory. So, it is at that moment, though refractoriness is also important, but for this particular application where the refractory is under load, the RUL or refractoriness under load is important, because both are temperature, but the refractoriness under load and the temperature corresponding to which is smaller than the refractoriness without load. So, that is an important property. Another important property is the porosity and slag permeability. Porosity and slag permeability. Now, as you know that there are molten phases, there are gaseous phases. So, the phases which are in contact with the refractory material, it should not penetrate into the refractory, otherwise some chemical reaction will occur and the refractory may collapse. So, for that purpose the porosity of refractory is important, because the porosity will determine the chemical attack of phases, for example molten slag, metal, matte and gases. So, it is for this purpose the porosity in a refractory is important. The refractory material which is in contact with the phases which I have written, it should not be porous. If it is porous, then these liquid will penetrate and accordingly the property of the refractory is affected, and it is possible some chemical reaction may occur between the component of the refractory and the penetrant, and as a result the refractory may deteriorating and it may fail under an application. Also, porosity is inversely proportional to strength. Higher is the porosity, lower will be the strength, but at the same time higher is the porosity, the refractory material will have a very low thermal conductivity. So, it depends upon the application of the refractory material. If you want to put the refractory material in contact with the phases, of course the refractory material should not be porous, but if the refractory material is to be put just to avoid the heat losses, then probably a porous refractory is desirable, because a porous refractory has a very low thermal conductivity. So, that means porosity decreases thermal conductivity. That means higher is the porosity, the material will have low thermal conductivity, and on account of which the insulating property of the refractory can be imparted by producing the porous refractory. Next important property is the strength. Naturally, the refractory material which are chosen, for example, to build a side wall or to build a hearth or to build the roof, it should have sufficient strength. That means the resistance of the refractory to compressive loads, tension and shear stresses. Otherwise, the refractory will collapse. Now, say for example, in taller furnaces, if you have a very tall furnace, so in taller furnaces the refractory has to bear a heavy load. The refractory has to bear a heavy load, and accordingly one should have a sufficient strength of the refractory is important. Therefore, strength of the refractory under the combined effect of temperature and load, they are important issue. Another important property is the specific gravity. Specific gravity. Now, specific gravity should be low to produce more number of bricks per unit weight. If the brick has higher specific gravity, its cost will be more, and if the specific gravity is high, the brick will be heavy. Well, heavy or lighter brick, it has to be selected as per the application required. Next important property is the so called spalling. Now, spalling of the brick is a very important property of a refractory material, because this corresponds to fracture of refractory. Spalling, in fact, it corresponds to fracture of refractory. Fracture of refractory. Now, this fracture of refractory, it may occur due to the following reason. Due to following or one of the following reason. Say, one reason is that temperature gradient. One reason is temperature gradient. Now, this temperature gradient may introduce thermal stresses on account of which the brick may collapse. Now, this temperature gradient, this may be caused either by sudden heating, or sudden cooling, both cases. That means you are heating the refractory and you are heating at a very high rate, and the refractory material is not resistant to the temperature gradient, then it may fracture. So, what I wanted to say is that the temperature gradient, it induces the so called thermal stresses, and any kind of stress that is being induced in the refractory, and if the refractory material is not resistant to those stresses, then it may spall. That is what the spalling tendency. So, one of the reason is the temperature gradient, and this introduces the called thermal stresses. Another reason is the compression in a structure. Compression in a structure due to expansion. Say, this means that if you have made a wall and if the refractory material is under compression, which may be caused on the expansion of the brick, then it will also introduce the stresses, and that may cause the spalling of the refractory material. Another reason could be variation in coefficient of thermal expansion, variation in coefficient of thermal expansion, between the surface layer, and the body of the brick, Now, this can be explained. For example, if this is the brick and this brick is exposed to the so called some of the slag, molten slag or molten metal, or some gases, then what will happen? These say molten slag or gas, and this is the brick and this is the surface of the brick. So, what will happen? This may react with it, slide deep into the depth, then on account of the reaction, the material which is on the top or surface of the brick is changed than of the interior one, and that may cause a difference in coefficient of thermal expansion, and on account of thermal difference in thermal expansion, again the brick may spoil. What I mean, these are the three reasons, or any reason which induces the so called thermal stresses or stresses of some kind, maybe due to the thermal expansion, maybe due to the temperature gradient or compressive stresses, any stress which is introduced in the brick, that may give the spoiling of the brick. Now, say on sudden heating, spoiling tendency is proportional to coefficient of thermal expansion divided by maximum shearing strain into diffusivity. Mind you, the spoiling is a very important property, and in this connection, say carbon, silicon carbide, graphite, high Al2O3, they have excellent spoiling tendency. They are excellent against the resistance to spoil, whereas the brick like high duty fire clay, forsterite is a MgO base refractory, they have a spoiling tendency so called good. So, that is what the spoiling means. Now, another important property is the thermal conductivity. Now, thermal conductivity of the brick, it determines the heat losses. It is an important property from energy conservation point of view, but if you want to have low thermal conductivity brick, then the brick has to be porous. So, porosity and conductivity, they are opposite. Higher porosity, low thermal conductivity, low porosity, high thermal conductivity. So, if you want to have a low thermal conductivity brick, that means the porosity has to be very high. So, accordingly strength and all these values will be affected. So, here the selection of the refractory is very important. So, these refractories which are of insulating in nature, they cannot be used wherever phases are in contact with them. They can be only used for heat losses purposes, one of the main objective of bricks having low thermal conductivity. Of course, chemical composition is important in the sense, as you recall now, the bricks or the refractory material, they comprise of SiO2, Al2O3, MgO and so on, and the same oxides are there also in the slag. So, if you have an acid slag, you cannot use basic refractory like MgO or CO based refractory, or if you have a basic slag, then you cannot use acid refractory like SiO2 or fire clay, because then the reaction will go on, and that is what the chemical composition of the refractory means. That means the chemical composition of the refractory, it must match with the so called, the chemical composition of the refractories must match with the composition of the phases, such that no chemical reaction occurs. That is an important thing. Next important property is the permanent linear changes. Permanent linear changes, which is also called PLC. Now, these permanent linear changes, they may occur on heating. If they are reversible or irreversible changes, accordingly this is an important property. Now, these permanent linear changes, that determine the so called volume stability, expansion and shrinkage, at high temperature. At high temperatures. Now, these permanent changes that can occur, they can occur due to, these changes can occur say due to say changes in allotropic form, changes in allotropic form. In many situations, the allotropic transformations, if they are accompanied by the volume change, then there is a problem of volume stability of the material. Also, these may occur due to chemical reaction, This may occur also due to liquid phase formation, or may occur due to sintering reaction. Now, sometimes this permanent linear change is advantageous also. So, while designing the brick structure, you may leave a space between the two brick, if you know very well what is the permanent linear change on heating, because if you leave the space according to its linear expansion, then on heating the brick will expand and it will rather fill the joint. So, that is also an important. So, this property is very important from several issues. One of the important, as I have just now said, so that is the important thing for permanent linear changes. Now, this permanent linear change in percent, it can be determined by determining increase or decrease in length and if you divide by original length into 100, that will be in percent linear change. Now, a knowledge of this is very important, or also PLC on percent volume basis, that will be equal to increase oblique decrease in volume divided by original volume into 100, that is also expressed in terms of percentage. So, that is about the permanent linear change. Another important property is the so called thermal expansion. Now, certain bricks, they expand when they are heated. So, in this connection, for example, if we see qualitative representation, say if I plot here if I take temperature as 0, that is only schematic, not intended to read the values from here, just to show the trend of the variation of thermal expansion. So, here this is percentage linear thermal expansion and plotted against temperature. So, you know, silica brick, this is the silica brick, it has very high thermal expansion. Very low thermal expansion brick, they are the carborundum bricks. This is the carborundum bricks. Carborundum brick, they are very low thermal expansion, and the carborundum is Al2O3 brick, followed by the magnesite brick. This is for the magnesite brick. Then the chrome magnesite is somewhere here. Chrome magnesite, and these are the aluminous fire brick. Aluminous fire brick. So, to conclude the figure, what we can say from here, that the thermal expansion of silica brick is greater than magnesite, is greater than chrome magnesite. I have just put chrome mag, is greater than aluminous fire brick, and is greater than carborundum brick. Carborundum brick. So, that is how this thermal expansion of the brick, that is an important thing for the, and these are the properties of the refractory. Now, remember, for one particular application, could be roasting or sintering or say steel making or iron making, you require a several combination of properties in order to find a particular application. So, it may not be possible that you get one refractory which satisfy all the requirement. No, it is not possible. So, therefore, depending upon the requirement, a suitable selection of the refractory has to be made. For example, if you are selecting a refractory where phases are in contact, then it is the porosity is very important. It is the refractoriness is very important. The penetrability is also very important. If you are looking for a refractory to just minimize the heat losses, then porosity should be very high, or the so called insulating refractory you are using it. So, what I mean, for a particular application, it is a combination of properties that is important, what is suitable for that particular application which you are looking for. Now, after knowing this, let us see now how the refractories are manufactured. Say manufacture of refractory. Manufacture of refractory. Now, remember, as I have said earlier, refractory material, they are not naturally occurring material. What I mean to say with that, that it is not that you dig a material from the mine and begin to use as a refractory material for that application. No, sir. Refractory material are not naturally occurring materials. However, they are manufactured from the naturally occurring material. So, that is an important thing. Though when they are manufactured from the naturally occurring material, then we have to take care certain material properties during manufacture stage. So, I will just draw in the form of the flow sheet, so that you can understand the manufacture of refractory. Now, for this, say we have the mined material. This mined material, that means what is coming from the mine, it is subjected to grinding or so called size reduction operation. Size reduction unit operations. It may consist of crushing, grinding, and whatever required may be. So, we have got the ground material, it is screen, I am avoiding that stage. The required material is taken and then it is subjected to to heat and calcination. That is, it is subjected to a high temperature, or it is the so called pre-treatment at high temperature. Now, why it is done? It is done to allow phase transformation, to allow phase transformation. As I have said earlier, they are the materials, and in the material have phase transformation, and the phase transformation is accompanied by the volume change. And if you put the material without taking care of the phase transformation during the production stage, then at the application the phase transformation will occur and the material may not be suitable for that application. So, the one of the objective of heating and calcination or the so called pre-treatment is to allow phase transformation to occur during the production stage itself, so that the refractory material which is being produced is stable at the temperature of application. Another objective of this heating and calcination is to allow allotropic transformation, to allow allotropic transformation. Now, remember, these allotropic transformations are also accompanied by the volume change, and there are certain materials which have a very high volume change, and if those allotropic transformations are not taken care during the production stage, then those transformations will occur at that temperature. So, of the particular importance, for example, if we consider quartz, for example, quartz, it is used for silica brick. This is unstable at high temperature. It is unstable at high temperature. And it forms the two phases. One is the tridymite, and another is cristobalite. So, these two phases are formed when quartz is subjected to high temperature. Now, quartz to tridymite, say quartz to tridymite, this particular transformation is accompanied by 16% volume change. By 16% volume change, that means there is an increase in volume, and this transformation occurs between the temperature range 870 to 1470 degrees Celsius. What does it mean? The quartz phase on heating, it transforms to tridymite, and there is a increase in the volume of 16%. So, that particular allotropic transformation must be taken care. Now, at temperature greater than 1470, the tridymite it transforms to cristobalite. It transforms to cristobalite, and there is a contraction of volume. Here the contraction of volume occurs. So, what is important in the stage of heat and calcination, that is to see the phase transformation, allotropic transformation, it must have been taken place prior to putting the material into the service. That is one of the very important case of heating and calcination. Another process or another important objective is, say, to remove water of hydration. To remove water of hydration. Now, for alumina refractory, bauxite is used, fire clay is also used, and fire clay has a water of hydration. That is, water of hydration means this water is in chemical contact or in chemical bonding with the main material. So, this water has to be removed, and removal requires a very high temperature in order to remove water of hydration. In case of magnesite, the naturally occurring material is MgCO3 or dolomite, CaCO3, MgCO3. So, those materials are to be dead burnt in order to remove carbon dioxide. So, another objective is to dead burn magnesite. To dead burn magnesite so as to remove carbon dioxide. It could be dolomite, or it could be MgCO3, or it could be calcium carbonate. Here CO2 has to be removed. Another thing, in fire clay, the mullite formation is important. So, in the pre-treatment stage, care is to be done so that the mullite also forms, because mullite is a phase which is resistance to slag, as well as it is imparts high temperature strength to the refractory property. After heating and calcination, now we have got a material which is processed further. Now, here this material is taken, and here this binding material are added. Binding materials are added into this calcined material, and this is subjected to give a shape which is, for example, dry. It could be dry or semi plastic or wet mixing. Any of the mixing method can be done, and all these, the product from all this is subjected to so called molding. Molding means to give a particular shape, and this I am taking to the next page. So, you have molding. Now, here there are different methods of molding, that is, you are preparing a shape, different shape of the refractory. So, this molding, you can have slip casting, hand molding, or machine molding. Well, machine molding is better for dimensional accuracy and whatever the advantage may be. So, the material from all these, the shaped one which you have got, it is further subjected to drying, because it is a green shape that you got. It has to be dried, drying, and for drying one can just do atmospheric drying, or one can go for mechanical dryers. Depending upon the applications or depending upon the size and so on, these are the important. Then it is further subjected to firing. Now, here the time temperature schedule of firing is very important. You have to go for firing between 1250 to 1600 degrees Celsius, depending upon the material under production, and this firing one can have batch or one can have continuous firing. Then subjected to cooling, then whatever rejections, they are being recycled, and these rejections, they are recycled for the process, and acceptors, they go to the customer. So, that is how these refractories are being manufactured for the so called particular application. Now, these refractories are for the shaped refractories, that means you are giving a shape. Now, here For example, if you are having a silica refractory, then quartz is used. If you are dolomite refractory, dolomite is used. Magnesite refractory, MgCO3 is a raw material, and so on, like that. They are the different raw material. If there is a alumina refractory, then bauxite or sillimanite or kainite, they are the raw material. Both kainite and sillimanite are heated till they transform to the so called mullite phase. The mullite is 3Al2O3 2SiO2. It is a very good phase or very good material, and it has a fusion point of the order of 1800 degrees Celsius. So, what I mean, these are the say some of these are, this is the method of production of the shaped refractory. Now, in recent years, the concept of monolithic refractory has also been advanced and used. Monolithic refractory. Now, these monolithic refractory, it is name generally given to unshaped refractory products. Unshaped refractory products. Now, these are materials, they are in the powder form, they are installed in some form of suspension, which ultimately hardens to form a solid mass. So, they are not like bricks, they are the unshaped material, and they are installed in place in the form of suspension, which subsequently harden and give you the shape whichever whatever is desired. Now, their types, they are available as castables. They are available as castables, that is, these castables, they are in fact mixture of coarse and fine refractory grains. Coarse plus fine refractory grains, and a combination has to be there, because fines will provide decrease the porosity as compared to the coarser grains. So, optimum mix of the different sizes is prepared. Then this mix is gelled by means of a binder system, and a green mass is prepared. The common binder which is used is the alumina content, and then they are installed. Now, these castables are, say, the installation of monolithic refractory, or the castables are, because they are in a sort of powdery form. Some binder is added so that it can provide the strength. Now, you have to install it. So, a certain method of installation are there. Installation, either we have free flow castables, normally they have low water content, or some gunning techniques are used. Some gunning techniques are used. That means, this mix is taken in a gun, and it is rather with the gunning technique, it is placed at the place of location, and then it is hardened. We may also, the castable, then we have coating refractory, so called coating refractory. These coating refractory are used to coat the working lining. Then we have refractory mortars. They are finely ground refractory material, mixed to form a paste. Form a paste. Now, these refractory mortars, they are used for laying and bonding shaped bricks. That means, if you have the two brick, you have to bond them, then these mortars are placed in between the two bricks, or for brick laying purposes these refractory mortars are used. Then another, we have insulating castables. Insulating castables. These insulating castables are used for cold face application. Cold phase application, and these insulating castables, they are manufactured from lightweight aggregates like vermiculite, bubble alumina and clay. They have low density and low thermal conductivity. Now, these monolithic lining, they are used for hearth making, and crack sealing. Now, say these are the two types of refractory which are being used. One is the shaped one and the manufacturing that I have said, and another they are the unshaped refractory. Now, unshaped refractory, they are become very common because they can be installed at a situ at a place, and a shape of the whatever shape is required, that can be obtained at the location. All brick laying and all these things are not required when you go for the monolithic refractory lining. Now, I thought I will give you certain example. Say for example, refractory for byproduct coke oven. Byproduct coke oven. Now, these modern coke ovens now very tall, around 7 meter height, higher coking temperature, high coke chamber volume. So, silica bricks are normally used. Silica bricks are normally used. Soaking pits. Soaking pits are furnaces which are used to heat the material below the melting point, and these soaking pit or the refractory material, it should have good load bearing capability, good load bearing capacity, high abrasion resistance, high abrasion resistance and resistance to FeO attack. Resistance to FeO attack, because during heating some iron may oxidize and accordingly FeO may form. So, these soaking pits bricks should have these three properties, besides temperature is of course important. Now, say top of the pit walls and soaking pit cover lining must be highly resistant to spalling, that is also important. So, here in the soaking pits, siliceous bricks are used, besides super duty brick, semi silica brick, castables and ceramic fiber lining are also suitable for cover lining. So, you see from here that a one type refractory does not suit the requirement of a particular process. Now, similarly, if you see rotary kiln, now the rotary kiln are used for the calcination of limestone in cement industry. Rotary kiln also used for calcination of hydrous alumina that is produced from the Bayer's process. Now, the whole objective of calcination is to remove the water which is in chemical contact with the material. So, in order to do that, a very high temperature of firing is required. Now, particularly for example, if you look the rotary kiln which are used for cement production, say rotary kiln for calcination, say for calcination of limestone and dolomite. Typically in cement industry, so these rotary kiln, they are 3.6 meter diameter, 75 meter long, and they rotate at a speed of 1 revolution per minute and inclined 3.5 degree to horizontal. So, it's a huge structure, and also the material enters from one end and discharges at the other end. There are different zones in the rotary kiln. All the zones are not subjected to same severity of temperature. The material enters at 25 degrees Celsius from the entering side and discharges at around 1200 or 1250 degrees Celsius. So, in between from the entry to exit, there are also different zones. I will not go into that detail, but what I want to say is that you may brickline with a very high quality material and unnecessarily increase the cost of the refractory material which may not be required. So, it is in this perspective, depending on the various zones, one can select the property of the refractory. For example, the high alumina or basic refractories are used, Here also temperature varies from 180 to as high as 1600 degrees Celsius. So, depending on the zone, one can also go for a zoned concept of lining of refractory, or one may line the same refractory, but lining same refractory will be very costly as compared to zone lining. So, what I wish to summarize this lecture is that by telling is that one has to select among the availables the right kind of refractory for a right application in order to save the cost. The objective ultimately is to have the high lining life, low maintenance at the economic rates. That is it.